This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Architecture, civil engineering.
No, no civil.
No civil.
Architecture,
Construction,
planning,
urban plan,
construction, landscape architecture,
yeah.
property.
Good evening, everybody.
Property management.
We're going to make a start. I know that there's still a few people checking in and getting in line, so I just have a few words at the beginning, and then we'll get started with the lecture. So good evening, and thank you for coming to join us. I'm Professor Donald Bates. I'm the Chair of Architectural Design, as well as being the Associate Dean for Engagement here at the Faculty of Architecture, Building and Planning. I begin proceedings by acknowledging the traditional custodians of the land on which we are meeting, the lands of the Wurundjeri, Wurrung people, members of the Eastern Kulin Nations. And I pay my respects to their elders past, present, and those emerging, and to all Indigenous and Torres Strait Islanders who may be witnessing this presentation. As a faculty, we want to acknowledge and affirm that Aboriginal and Torres Strait Islanders people had and still have laws and laws that predate colonization. As built environment and design experts, we join in their responsibilities to care for country and thank our traditional owners for sharing their knowledge of country. Tonight we present the third Dean's Lecture Series for 2023 with guest lecturer Professor Chimay Anumba. His lecture will focus on the growth of digital twins and the potential role they play in the transformation of the construction industry. Professor Anumba is the Dean of the College of Design, Construction and Planning at the University of Florida. He holds several doctorates, including a PhD in civil engineering. He is the recipient of the 2018 ASCE Computing in Civil Engineering Award and is a member of the U.S. National Academy of Construction. Chimay has over 500 scientific publications to his name, has supervised over 50 doctoral candidates, and has mentored over 25 postdoctoral researchers. He will draw on his clearly very considerable expertise to discuss the background on the growth of digital twins, drawing on examples from research prototypes to highlight their key features as well as benefits. We are really very pleased to welcome Chimay to the university this week, and particularly in line with the fact that he's just come through some major weather events in Florida to get here to join us. So thank you very much, Chimay.
Thank you.
I give you the floor.
Thank you. Good evening, everyone. It's always a pleasure to be in Melbourne, and I'm most grateful for the invitation to share with you some of what we've been doing at the University of Florida, and I'm really pleased to see so many here tonight. So I'll just launch straight into the presentation. I chose to talk about digital twins for buildings and large capital projects, and I'll try to give some examples of what we've been doing, but then also leave some opportunities for questions, and then also try to acknowledge some of the other work that others are doing as much as I can. So by way of an outline, I'll start with some introductions and then talk about some definitions and some classifications. And then I'll talk about what we've been doing, starting with some early cyber-physical system DT applications, and then some more recent work that we've been doing, and try to draw some conclusions, and hopefully we'll have some time at the end for questions and discussion. So I've always said that Melbourne is one of my favorite cities in the world. I think this is probably my fourth visit, but it's such a livable city, and I think that there are lots of opportunities to advance the planning of the city and leverage some of the emerging technologies. So the idea of the context for what we are doing is really the fact that there's a lot of interest in what people call Industry 4.0, the fourth industrial revolution, and some already are talking about the fifth industrial revolution. But all of that really is embedded in the fact that there's a lot of technological advances, And with that also comes a lot of evolution in working practices. And while a lot of people do not see the construction industry as one that is evolving very rapidly, there is certainly a degree of evolution. And then over the last 5 to 10 years, there's been a big growth in the adoption of building information modeling across a lot of different countries, some pushed by industry trends, others pushed by government mandates, and others really pushed by companies wanting to be a lot more competitive relative to their peers. But now we are talking about the need to go beyond BIM and to look at how much more we can leverage technology. And so the interest in digital twins is growing across several industry sectors, and construction is certainly not wanting to be left behind. So what exactly is a digital twin? There are lots of different definitions, but I chose this particular one because it seems to capture all of the different elements, which is really looking at a digital twin as an integrated multi-physics, multi-scale probabilistic simulation of a complex product that uses the best available physical model, sensor updates, and so on, to mirror the life of its corresponding twin. And you'll see from the diagram here the number of critical components. One is you have to have a physical product, which is, oops, sorry, I think I moved too quickly. Okay. Yeah, so there's the physical, where's the point? Yeah, on the side.
So this little red piece here.
Okay, I pushed that and it seems to move. Okay, right. So, so there has to be a physical product, which is represented on this left-hand side, and then a virtual model or the digital model, and then some means of connection between the data and the information. And so basically what you see is what is generally referred to as a cyber-physical system, which is really integrating the physical with the cyber. And the critical thing is the bridge between the two. And so when you look at the diagram here, basically we are talking about having some tight integration between the physical and the virtual or the digital. And so you have a number of things going on in the physical. You have sensors that capture what is going on, and then you pick up data, which you can run some analytics on, and then you can then use actuators to then carry out additional changes to the physical environment. And so this is the physical and the cyber working in sync. And very often we kind of refer to this as the hardware in the loop kind of configuration, where you create a model based on a number of assumptions, and then you actually then build a physical prototype. You run it and you capture physical data on actual performance, and then you use that to recalibrate your digital model. And so some of the main features include having real-time reflection and some level of self-evolution. And the extent to which this happens obviously depends on how sophisticated your digital twin model is. And so the concept of digital twins originated back in the 70s with the Apollo program, and that was where the idea of the twin concept came up. And the first definition actually dates back to 2010, when NASA formally defined a digital twin. Now, over the years, there have been a lot of applications in manufacturing, in industrial engineering, in robotics, and now increasingly in construction industry. We are becoming a lot more interested in this. So there are lots of different classifications of digital twins. And again, these are based on lots of different elements. It could be based on the degree of data maturity, the data type or class, or the application area. But all of these classifications really are intended to help highlight the digital transformation value of these different types of digital twins, and also to clarify the implementation requirements. But usually, people look at all of these taxonomies as continuums, which you'll see from the next two diagrams. So one of these, this is one that is from Autodesk, and you can see up to 5 different levels of digital twins, starting at level 1 with what is called a descriptive twin, which is basically a visual replica with live editable design and construction data, including 3D models and BIM. So at some level, you could regard a BIM model as being a descriptive twin. And then you go all the way with increasing levels of complexity until you get to what is known as level 5, or the autonomous twin. So with level 2, it's an informative twin. You're beginning to integrate sensors and operations data. With level 3, the predictive twin, you're beginning to capture real-time information as well as contextual information analytics to identify potential issues. Level 4, the comprehensive twin, you're leveraging advanced modeling and simulation to explore potential future scenarios, as well as prescriptive analytics and recommendations. And then level 5 is when you start to integrate a bit of artificial intelligence to enhance the capacity to learn and make decisions. So there's a lot of different levels that you can go with digital twins here. Another classification is based on, it's adapted from KPMG, and this is where you start with the digital twin classification, starting with what is called the existence twin, and then you go all the way to cognitive twin, and it's kind of similar to the classifications you would get with the Autodesk, the previous classification. And so basically the BIM model, again, is really at the outset basic existence twin. And then when you start to add IoT devices that can capture the status of a physical product and the condition, and then start to add a number of elements of historical data as well as actuation, then you're sliding all the way up the chain from the existence twin to an operational twin. And when you include physics-based analytics, then you start to look at a simulation twin. And then when you embed artificial intelligence, you end up with what people refer to as a cognitive twin. And so these are lots of different levels, but also you grow in complexity in terms of the data types, from properties, location, condition, work, cost, capability, utilization, and then right up there you start to look at performance data. So it's really a continuum, and a lot of things that are described as digital twins will fit somewhere along this continuum. Okay, so from our perspective, in terms of the research that we've been doing, we see the key elements of the digital twin or cyber-physical system approach as really being the bidirectional coordination between the virtual model and the physical construction. And a lot of people often get confused when we talk about cyber-physical systems and digital twins. I think the term cyber-physical systems was probably better known and existed more in the scientific community before digital twins actually had a lot more industry buy-in. But essentially, every digital twin is a cyber-physical system, but not every cyber-physical system is a digital twin. So I think that is something I'd like to get clarified up front. And so we've been dabbling in this area, and I use the word dabbling very clearly because we don't consider ourselves really experts. We are just trying out a number of things. And in the early days, one of the things we wanted to do was to look at focusing on this bidirectional coordination, how can we track construction components and make sure that they're actually in place on a construction project? And how can we also look at use of digital twins and cyber-physical systems to monitor temporary structures? And then having done that, we moved on to mobile crane safety and efficiency. So I'll talk about each of these quite briefly. So the idea with automatic component placement tracking was really that that was probably our very first project. And so the intent was, let us make sure that there's this bidirectional coordination. So we actually built a physical tabletop model of a little building, if you want to call it that. And then we created a digital model of it, and we attached a number of different sensors to it. And so, for example, we could remove some of the components like a door or a window, or even lift the roof up, and then it will automatically show on the digital model that this was no longer in place. And that was just enabling us to make that coordination. And then conversely, we could actually write information on the sensor, which we could then read from the digital model. And so that helped us understand that we had that bidirectional coordination. And so having done that, we then tried to do that with some light fixtures in our building. And so we were able to tag specific light fixtures to our digital model of a particular room, and then we're able to manipulate the light fixtures so you could turn the lights on and off from the digital model without going into the room. But also, if you had defective light fixtures in the physical environment, then you could actually also detect that in the virtual model without going to the room. So those are some of the things that we tried at the early stages. And we tried to do something different, so we started to think, okay, how can we apply this in another context? And one of the early ideas was to look at temporary structures. The idea of temporary structures was based on the fact that there were a lot of safety issues associated with temporary structures, but also some of the learning that we got from playing around with temporary structures, we could apply to some of the types of structures. And so our work focused on really using scaffolding as an example. And so we had a physical laboratory mock-up of that, and then we developed the virtual model. And we were able to then link the two such that if there were any changes in the physical environment, we could actually detect that in the model. And we introduced some of those changes by loading some of the members and tracking when they reach certain levels of loading. But also we could do things like remove the bracing and then detect that the bracing was no longer in place. And that would generate an alert. And my student developed this phone-based app that showed what was actually happening. So the project manager, whoever, could get a simple alert that said there's a problem with this particular member. Okay, so the next thing we looked at was we'd done something with basic component tracking on a project, then we did something with temporary structures. So we thought, okay, let's try to apply this to equipment. And one of the areas that was particularly problematic on many sites, and I don't know if you had as many problems in Australia as we had in the US, but there are lots of mobile crane failures, mainly with problems associated with stability and overturning, collisions, falling objects, or the crane striking people or vehicles. And so we thought we could use cyber-physical systems and digital twins to address this. So we had a project funded by the National Science Foundation. And so what we did was to develop a simulation model within which we integrated a number of the critical safety rules. And we're able to do things like detect the potential for the crane to overturn, and then also look at the capacity, make sure that there was no overloading issues, and we could actually track all of this and then provide proactive feedback to the crane operator. And so we're then able to go on a site and actually track the lifting operations in real time, and then be able to simulate those as well. Okay, so more recently we've started to do some other stuff. We're always looking for slightly different problems that give us more insights into how we can apply this. And one of those areas was with regard to healthcare facilities management. Another was what we ended up calling the financial digital twin for public sector capital projects. And I'll talk about that in a moment. And then we are currently working on a digital twin for predictive maintenance. So for the DT for healthcare facilities management, we looked at a case study based on one of the University of Florida's health facilities, which we call the Oaks. And there are 3 specialty practices involved in this particular location. One was the ophthalmology, otolaryngology, and audiology, all in this location. And the first thing we did was to look at what are the different scenarios that play out in these sorts of healthcare environments. And we came up with about 6 different potential scenarios, which we then validated with experts in the field, and ended up with selecting 2 that we could implement. And so those 2 were one related to monitoring and controlling the HVAC system, and the other was monitoring the IAQ in the room to enable specific equipment to perform. And so the intent is really, with the first scenario, it was about monitoring the pressure as well as other elements in a particular room. I think it was an operating room, and then the other was in an MRI room. And so the intent was really to detect any sort of changes in the performance of the system, and then to alert the FM manager, who would then take corrective action. And the same applied to the monitoring the indoor air quality for equipment performance. Now, I'll mention this up front because one of the things we intended to do was to have automated adjustments to some of the equipment. But this being a healthcare facility and this being a research prototype, they did not trust us enough to allow us to do that automatically. So we kind of fell back to simply notifying the facility manager when there was a problem so they could then step in. So you may find that in some of your projects that you don't have the full level of automation that you desire. And so this is a typical 6-layer system architecture, going from all of the different elements, the physical sensing, communication, application, and actuation, and then a device layer. The actuation, as I said, we did not actually actuate anything other than to alert the manager that there was a problem. And so one of the things we needed to set was the boundary conditions for the operation of the different things. And so for the operating room, we had different boundaries for high and low pressure. We weren't monitoring carbon dioxide, we were monitoring temperature and relative humidity. And then for the MRI room, we were focusing more on carbon dioxide, temperature, and relative humidity. And then we used a set of hobo sensors, and that is my PhD student in the blue suit there, setting everything up in the facility. And so we ended up doing some testing. This is just a model of the digital model of the healthcare facility, showing the location of the 2 rooms of interest. And then we're able to import that into a Unity 3D environment where we could do a lot more simulation and playing around with the model. And again, we focused on those two specific scenarios. So what we did was to figure out how to communicate the different changes when there were problems. And we used a very simple system that my student came up with, which was to have different color codes that showed when certain elements were out of the acceptable ranges. So for example, if pressure was high, then we had the color in red in that room, or purple or orange, and if you had multiple, and then this was when they were low, and if you had multiple things going on, then you would show that as black. And then we did the same, and this shows high CO2 with the excuse me, with the color purple in that room. So we ended up, as we always do, we try to evaluate this with potential end users. And from this, you can see that it was pretty good feedback. They thought it was easy to use, very interactive, very informative, and they also thought there was a level of excitement to what they could do with this. Okay, so here's another project, and this is more of the kind of large capital project scenario that we're looking at. And this came about because we got into conversations with the Greater Orlando Aviation Authority, and they had this $3 billion South Terminal expansion. We were just working with them initially and looking at how we can best leverage the use of BIM on the project. And so we had 4 grad students looking at different aspects of integrating BIM with their facilities management, integrating BIM with their GIS, and then also integrating BIM with aspects of financial management and cost tracking. And so one of the things that came out of that was really this need to track the different sources of funding on these projects. And so by public sector, we mean these sorts of facilities, health, roads, aviation, schools, utilities, parks, and so on. So when you're dealing with large capital projects, there's always an element of managing public funds. So stewardship is very important. And that means there's a burden of financial or fiscal responsibility associated with these projects. And there have been lots of situations where problems have occurred. Now, given that construction is often long-term and complex, there's a need to look at not just the phase that most people are concerned about, the design and construct, but then also to look at operate and maintain, as well as long-term assessment. So people focus on planning and budgeting and then going on to design and construct with not as much attention to the other 2 phases. And so when you have multiple funders for these projects, then typically they have a number of different restrictions. And so in the sort of public sector and airport kind of environment, the sort of funders you could get could be federal dollars, state dollars, some private investments, some loans, and then also some local municipalities that would provide funding. But all of these have certain restrictions. So for example, if you're doing an airport, you cannot use federal funds for anything other than airside operations. That's one of the major restrictions. And so it's very important that you avoid mistakes because they can be very costly. And there are examples where an organization has misused $38 million. They've lost a lot of funding because of that. They've had to repay the $38 million, And the actual probe that followed all of this cost about 252 million. So just from a simple misappropriation of public funds. And so it's very important that organizations get it right. So we thought we'd try to fill the knowledge gap in this area with this specific application. And so what we came up with, initially we called it the colors of money, or the color of money. But then we ended up devising a system whereby you could basically attach an attribute of funding source to your BIM model, and you could show exactly where the funding is coming from. So because airports are highly sensitive projects, I'm not using an example from the airport, I'm using another example from a separate building that shows what we try to do here. Okay, so this is a short video that I'll try to run. So you can click on that and it shows you all the different sources of funding, including all of the restrictions. And then you can use a color palette to assign them different colors to all the different sources, and then you can display your model that shows where all of the different sources of funding are coming from. And so you can very easily see at a glance where the different sources of funds are occurring in the building, or in the facility. So if you see a color that is not appropriate, say for in some other area, you can actually identify that there's a problem. But you can also use this in a proactive way to identify which sources of funds you need to go after in order to get all the funding you need for a project. So that's one particular use of this that we found. Again, we did some evaluations which showed that with regard to initial planning, visualization, and task automation, and the practical use of this, this was very useful. Okay, so the final one that we are currently working on, this is work in progress, is related to predictive maintenance, and is predicated on the fact that a lot of organizations, particularly public sector organizations, have a lot of deferred maintenance. And so we're looking at how do we try to look at that and then help with decision making by being a bit more predictive in terms of what is going on. And so we first had to select some implementation tools. And here we basically have a digital model, but then in order to make it work effectively, we need to look at IoT platforms as well as game engines, and then the number of commercial plug-and-play tools that can also be used. And for this particular application, we're looking at an existing building of the College of Business at the University of Florida, for which we already had the digital models. And so we chose to use the Microsoft Azure Digital Twin IoT platform and the Unreal Engine to play around with that. And as I'll say a little bit later, we do have a partnership with NVIDIA, and they have an Omniverse system, which we are going to be using on a couple of other projects. So, so this is the system architecture for this. It's fairly complicated and difficult to read, but basically we do have that interaction between the basic Revit model and then imported into the Unreal Engine, and then there's an ADT plugin, and then we have the back-end systems for our building automation systems, and then this allows us to capture what is happening in real time, and then also to be able to make some predictive maintenance decisions. And then within Azure, you can create these twin graphs, which establishes the relationship between different assets, and then it also supports a number of structured queries. And so with this, you can interrogate any of these. This represents a lot of air handling units in the building and a number of building automation points. And then you can see the graphical representation of the interactions between the different systems. And there's a short demo here, which is basically showing what we are doing with this. This is incomplete, so it's just going to show you a little bit of how we are trying to capture the information from some of the sensors in the building, and then trying to make sense of the data that is generated within that. And then based on that, we can then make decisions about what elements need some maintenance if they are not performing at the right level. So there's a lot of different air handling units that we are tracking here. And we're looking specifically in this demo at temperature and pressure. And you can click on any of those specific sensors to show you the data associated with that. Okay. So we've looked at a number of different aspects, and we've learned a number of lessons. And so I think one of those is the fact that it's essential to have a very clear application domain. You need to know exactly what you are trying to capture, and then it's very important to have accurate and up-to-date virtual models. You need to be careful about how you design the mechanisms for bidirectional coordination between the physical and the virtual. And then also you need to be very careful about the choice of sensors or sensor networks and the associated platforms to deliver those. We found that being able to carry out laboratory experimentation prior to trying it out on real projects was very helpful because you could iron out a lot of critical things relating just to the performance of the systems before you actually roll it out. Was very helpful. There are lots of practical considerations that are involved in moving from a lab prototype to real-life implementation. So, for example, with the very first one that we did, one of the things we found was that there are lots of, we're trying it out in a lab within a building, and within that there were lots of different wireless networks. So we had a lot of interference, and we needed to figure out how to filter some of those out in order to make sure that the system behaved effectively. But then you also have issues of scalability, cost, power, and a whole range of other things. Okay, so where we are going with this now, we're beginning to look at how to help our university to roll this out on future and existing projects. And so we're working on developing a protocol for the deployment of digital twins across the campus. But also we've been partnering with one of our alumni who's been very much in this area, and he's formed a startup company called Immerser. And they've been using this, particularly at the urban scale, to do multidimensional analytics. So I'm going to show a little video clip that shows some of what they've been doing. And this is based on a specific project in Tampa, Florida. It's called Water Street. It's more of a marketing thing, but I think it will illustrate some of the critical elements of this. So that shows a whole range of different things that you can do, and you can aggregate a lot of the data. And this was built using the Unreal Engine platform, which we are now integrating into a lot of courses and our programs. Okay, so I'll wrap it up. So I do think that digital twins offer considerable benefits. There are numerous applications that are being developed, and I've shared some of research prototypes as well as what is going on increasingly in industry. There are lots of potential benefits, starting with real-time process tracking and active component control, reduction of risk, more accurate as-built models that can be used for operation, facilities management, deconstruction, and a whole series of other things. But then also increased capacity for what-if simulations, improved opportunities for sustainable construction practices, improved safety through proactive hazard monitoring, as well as opportunities for cost and time savings. And these are just a few. If you look at the literature, you'll see a whole lot more. And so really the bottom line is the construction industry needs to be a lot more proactive in adopting digital twins. So some of the examples that I've talked about are captured in a couple of books that we developed. The first of those is Cyber-Physical Systems in the Built Environment. It does include some examples that are from transportation, the energy sector, and a number of other areas. And then we did this research companion to building information modeling, and then we have a number of chapters within that that are dedicated to cyber-physical systems and to digital twins. So, and then, are there any questions?
So thank you very much, Professor Anumba. So we do have a little bit of time to take some questions. I believe we have some microphones for roaming. So does anybody have a question for Professor Anumba? We have one down here.
Thank you, Professor, for your great presentation. For implementation and adopting these systems, these platforms, do you see that becoming part of the builder's scope of work, part of the FM team's scope of work, and even consultants to some extent, because that's where the BIM model kind of starts to come to life? Yeah. And where does the evaluation of these systems in terms of if they're ready for delivery to the FM team lies?
Thank you very much. That's a very good question. I think that increasingly these are becoming part of the scope of work. And I'll give you an example because we're in the middle of a very real project where we have an addition to our college building. So we have a 50,000 square foot addition to our college building. And one of the things that we had written into the brief or into the program was that the design consultants would deliver a digital twin ready model for the building. And so, but to do that requires a whole series of things that they can't do by themselves. And so what we found is that we are now having to engage with some of the software vendors, and they're going to partner with us to making sure that we actually have a fully functional digital twin that's integrated with a very high density network of IoT sensors that we're having embedded in the building. So it is a partnership, but again, one of the critical elements of that is making sure that we carry our facilities management folks with it, because they were very nervous about all of this. And the question was, how are we going to maintain this? We don't have the in-house expertise, and so we've been working very closely with them to figure out what is the best platform, what will be the necessary training, and other things we need to put in place. So when this is done, it's actually ready and available for them to use. So it's not like a TV set you buy and you switch on and it automatically works. There's an element of preparation that needs to go into it, starting with making sure that the basic digital model has the level of detail to development to be enhanced into all of those different levels of the digital twin that we talked about. And so we're actually living that with our new building, and then we are also looking ultimately to have a cognitive digital twin, because we do want to embed some AI and machine learning into the model so it can be a lot more useful long term.
Anybody else with a question? Yeah.
Thanks. And again, thank you so much for the presentation. Now, I sense that the openness of how you and what you define as a digital twin is at the same time potentially its downfall, because it can mean so many things to so many people. You did show us two sort of very rudimental sort of breakdowns. In the BIM space, we had very similar issues where we were asked for to deliver full BIM by someone. And I guess now we have issues where somebody might request a digital twin from a government side, which means something completely different. You showed us so many different examples today. So do you think we need to codify much better what we mean when we say digital twin, depending on which of the 5 or whatever 7 different types, but also which level of development? Do we have to become much clearer about defining what their content actually is and their purpose?
I would agree with you to some extent in that without definition, we have a lot of people running around describing their BIM model as a digital twin. And if you look at the taxonomy that I presented, they are right to some extent, because it is the first step along the way. But I would never define a BIM model as a digital twin, even though it's the very first step. I do think you need to have a whole lot more to it before you call it a digital twin. It is a digital representation. Some people would call that the existence twin or whatever, but I think to have a real digital twin, you do need to have those elements that I talked about, which is really having that bidirectional coordination between the model and the physical artifact. And so yes, some greater specificity in definition will be helpful when we are talking about these things, but that actually is helpful at one level, but at another level it could be problematic in terms of halting the move. Because if you say to somebody, you're not doing digital twin, put away your BIM model, don't touch it, they kind of get discouraged and they don't even start to move along that continuum. So we need to be careful not to stop people experimenting, but also to have greater clarity when we're actually marketing these systems and tools.
Thank you. Professor, first of all, a fantastic presentation. Thank you for that. I'm happy that you mentioned facility managers, because I happen to have some close connections with the Facility Management Association here in Australia. And the discussion is that they are, in fact, eagerly awaiting the realization of what we call smart buildings, or buildings that can talk to you, give you enough information for decision making. But the problem is that while we do have the technology, the design has not really integrated with the facility management stage. What is your experience or advice on that? Have you seen good applications in that?
Yeah, I do think that that gap is closing. Increasingly, we have a lot more facilities teams that are beginning to use BIM models. And this goes back to basically what happened at the early stages. So, for example, when I was at Penn State, we came up with the BIM project execution planning guide, which we developed basically for project teams to be able to deploy BIM for a variety of what we call BIM uses. Now, we developed it as a generic framework, and then a lot of people have customized it and used it for their different uses. Now, having developed that, what we then found was that the real issue was not with necessarily the project team, but more with the clients or the facility owners, because people were learning about, we need BIM on our project. Okay, so they said to the project team, give us a BIM model. But they didn't have a clue what to do with the BIM model or what functionality was needed in the BIM model. And so at the end of the day, they got handed some model on a CD or whatever, and they didn't have a clue what to do with it. And so what we ended up doing was to go back to develop what we call the BIM for Owners Guide, which was really to help owners to think about why do they need a BIM model. So you start with the business case for using BIM on a project. Then talk about the legal regulations surrounding all of that. Then talk about the functionality you want in a BIM model. And then you also talk about other considerations such as how do you integrate the BIM model with your back-end systems, with basic FM systems. And so with that, now owners are not just saying, give us a BIM model, but they are saying things like, we want a BIM model that can integrate with Maximo, FM system. And so it's becoming a bit more specific and a bit more useful. And so that gap is narrowing, and I think digital twins will help even more because they can manipulate things in real time, as well as run what-if scenarios without actually having to implement them in reality. Yeah. So I'll give you another example. With our new building, for example, there's so many things we can do with the level of the density of IoT sensors in terms of tracking occupancy in the building. We can even move chairs around to make sure people go a certain way through the building. We can, based on traffic patterns, reconfigure different parts of the building in addition to monitoring energy use. There's just so many different things we can do. We could even do some end user behavior, occupant behavior analysis, play around with the temperatures. Do people open windows when it's really too cold in Florida? I mean, in the room, in order to let hot air in, because Florida is often hot, or do they put on additional clothing? Those sorts of things we can play around with.
So we have just time for one more question. Mark.
Thank you, Professor. So thank you for the clarity of your lecture on a complex topic. I was particularly taken by the elegant financial digital twin and the way in which you colour-coded in a very clear and elegant way the funding components of the building. So my question is, who were the major beneficiaries? Were it the project team? Was it the accountants, or was it the levels of government seeing where their money was spent? Yeah,
I think the biggest beneficiaries were really the owner organization. And we developed this for the Greater Orlando Aviation Authority. They were the clients who were building the airport. And so they got all of these different streams of funding. And so they needed to be able to keep track of what funding was being used for what. And we could have them display that visually. So for example, if you see any federal dollars bleeding into the actual building as opposed to the airside operations, you saw that immediately. But then also, as they were raising funds for the facility, they could actually determine what proportion of funds were needed for the different parts of the building. And so there really was no point going for more federal funding if you already had enough for the airside operations. So you could use it proactively rather than retroactively to figure out what you really need, but also in a forensic way to figure out where have we used this and do we have a problem? Yeah.
Great. Thank you very much.
Thanks very much.
Just wait here for a moment. I just want to provide a little bit of information on some upcoming events that we'll be hosting here. On the 11th of September, we'll have a new exhibition in the Dulux Gallery, Matrix, How We Live Now. And then we have a series of public lectures that are coming up in various lecture halls here within the MSD Glenn Davis building. And our next Dean's Lecture Series will take place on the evening lecture will take place on the 3rd of October, Sense of Identity with Landscape Studio, which are Chloe and Michael Humphreys in landscape architecture, with some of their work in East Africa as well as some of their work in Europe. And we want to thank you for coming, but first, can we give a big round of applause to Professor Anumba? So thank you very much for being here this evening, and please keep in contact with our website and link to find out about other events and activities that are happening in the coming weeks. Thank you.
Thank you very much. Thank you.